IFEP, and I hope all of you know IFEP, International Federation of Information Processing. At least this I got right. Sometime before he was director of the software engineering lab at NASA, so it's a space agency in America. And now he will talk about formally specifying data collection missions and space exploration. So space is still his main interest.
Thank you, Wolfgang. I think I can use the mask off speaking, right?
No, you can remove it.
Okay, thank you. Yes, so thanks everyone. As Wolfgang just said, I spent 15 years as director of the NASA Software Engineering Lab, and then I moved to LIRO, which is a software engineering research center based in 9 universities. But my interests have stayed with the use of autonomous systems in space exploration. That's the main area that I work in. But my background is in formal. That was why I was hired into NASA in the first place. So this is our neighbor that draws a lot of attention. The idea that there was life on Mars actually goes back to 1877. An Italian astronomer saw lines on the surface of Mars, which we now know to be mirages. They don't actually exist, but he called them canali. And people mistranslated this as canals, and as they were building the Suez and Panama canals at the time, everyone thought that there were these big concrete structures on Mars, and therefore there had to be intelligent life. And the first attack from Mars is from The War of the Worlds, which is a book from 1894 by H.G. Wells. This is actually the cover of the LP of the musical version, because the covers of the actual book are pretty boring. They just say War of the Worlds. And you probably know the story that in 1935, Orson Welles did a broadcast of the book, but they didn't tell people that it was a novel, and they thought it was a real news story, and they thought the world was really being invaded by Martians. But the idea of Little Green Men from Mars comes from a book by Edgar Rice Burroughs, which was published in 1912 as a serialization, and then in 1915 as an actual book. But he didn't describe little green men, he described 16 feet tall green men with 6 limbs. But that's where the idea of green men from Mars comes from. And of course, since 1997, we've put 5 different rovers on Mars with great success. They've all lasted longer than was expected. And the most recent one also included the helicopter, Ingenuity, which we'll talk a little bit about in a few minutes. And the most recent advance in space exploration and space data collection has been the JWST, the James Webb Space Telescope, launched on Christmas Eve last year. This is the actual telescope. It's not a mock-up, it's not a model, it's the real thing, it just doesn't have the lenses in it. And this is the team of people who built it, and that's me. You can't quite see it. And the big, of course, goal in space exploration right now is to launch what was originally called Constellation and then later Orion, and now it's Artemis, the twin of Apollo. And this is to be the largest software project ever. The estimates when it was first being spec'd in 1999 were $8 billion US. Okay? That would have made it the largest software project ever. Whether it would cost more or less now is actually quite hard to determine, because we've had so many advances in technologies and tools, but then we've also had so many advances in expenses. So we don't quite know, but it was planned to be the largest software project ever. But what we're trying to do is build space exploration missions that last, that are resilient. So they're some of the most expensive missions ever. Think of $8 billion US. And they require huge levels of autonomy, and I'll explain a little bit of that to you. And the consequences for failure are great. First of all, most missions are 20 to 30 years in the planning process before they launch. So that means you have 20 to 30 years of work lost. We're talking about billions of dollars typically. To launch a Delta rocket, which is the rocket that was used for Apollo, costs about $100 million just to launch it. So think of the amount of money that's involved. And the biggest issue is that if we fail in a mission, the impression with the public, the taxpayer who is ultimately paying for all of this, is dreadful. And people forget that NASA spend more than half of their budget monitoring the Earth, and there is a law that anything NASA invests money in must produce a technology that can be used in a non-space domain. So obviously if we're developing satellites and cameras and things that can take pictures in space, this has many applications on Earth as well. But the one I like to tell people is the rumble strips on the side of motorways. You know when you go to the edge of the motorway and it goes boom, 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 boom? NASA owns the patent on that. So every time a new motorway is built, they make money out of it.
My quick question, does it mean that all software that NASA develops is open source?
No, there is a move towards open source, but there's not a requirement for it to be open source.
Okay.
And it is quite common for there to be an open source version and a non-open source version.
Thank you.
Yeah. This is just a chart from the NASA Controller's Office, that's the Chief Financial Officer, and basically what it shows is the investment that NASA puts into its requirements and its planning processes and the cost overruns. So when NASA puts about 2% into its requirements, it has a cost overrun of about 200%. When it puts about 15% of the budget into requirements, it has about a 5% cost overrun. I believe this curve to be the right shape, but it should be up and to the right, because most NASA missions run about 800% over budget. Okay, so at $8 billion, 800% over budget, it's pretty expensive. The red dots correspond to NASA missions. They're not confidential. There's no names on them because it's just illegible otherwise. But the dot at the middle is the Hubble Space Telescope, just to give you an idea. So we've been working since the late 1990s on swarm technologies, what nowadays most people call drones. We never use that term, but that's essentially what they are. And we're looking at using something being inspired by swarms of bees, colonies of ants and termites and flocks of birds. We don't know exactly how these work. We have theories about how they work, but we don't know exactly how they work. But we do know some of the things that they do. And so these technologies have been used in many areas, not just drones, not just physical devices. It's been used in drug discovery. A colleague tells me that it has brought drug discovery down from an average of 17 years to about 4 years. It's used widely in communication systems, particularly video on demand, environmental monitoring, especially by NASA in monitoring lakes and oceans and rivers, etc. And of course exploration, not just in space, but also mining and areas such as that. So the idea is that by having a number of small spacecraft, you can make better use of solar power, and battery power is always a big issue for NASA. You can go to places where you couldn't send a large spacecraft or a large rocket. You can do more complex things, such as taking X-rays, which requires 2 devices, which you can't do with one large rocket. And you have greater accuracy and flexibility as a result, and you have resilience. So you have the ability to last long-term in space. Some damage doesn't mean the loss of the entire mission. And again, 20 to 30 years in planning, 100 million just for the launch, you don't want to lose something. So we've been looking at how we can use swarms of intelligent spacecraft, drones if you like, to do various things. So we have a mission called Autonomous Nanotechnology Swarm, or ANTS. So one is it has 3 submissions, and we're adding a 4th and a 5th. The first submission is to go to the surface of the Moon and Mars and collect in a day what the rovers have collected in all the time they've been in Mars since 1997. Going to the rings of Saturn to collect information about the gases in the rings, and the more interesting one and the more complex one is to go to the asteroid belt and to learn more about the contents of asteroids, and in particular, as NASA has set itself a goal of putting a human on an asteroid, this is particularly interesting to us. So these are the sort of devices that we plan to use. These are called tech walkers. So it expands out and it basically works by falling over. It transfers control from each node to the next node and falls as a result. And as it does that, it can go over rocks and craters and rough terrain. We can add various devices to these, like cameras, X-rays, etc., to collect information. And we can connect a number of them together so that we have essentially a caterpillar that can carry loads and bring equipment and so on with it. So that's obviously an animation, but here's the real thing. So this one can shrink down to be a 30-centimeter cube, it can expand out to be 2 meters tall, and it can climb the outside of a 5-story building. It's quite fun to see people panic when they see this.
Not as elegant than the animation.
Yes, but remember, gravity is different. And I should say, you know, a a previous administrator of NASA in the early 1990s had a policy, better, faster, cheaper. And that is absolutely true in this case, because by the time this launches, it will be much better, much cheaper, and it will be much more efficient and faster. So the PAM submission is to send a large spacecraft to L1. It's a point in space, the Earth-Moon Lagrangian point. From there, there is effectively no pull on small enough devices. So it will eject 1,000 spacecraft, and then from there, gravity will pull them into the asteroid belt, taking about 2.5 years to get there. They form themselves into various subswarms, collect various types of data from asteroids of interest, and then send that data back to Earth. You'll notice that the arrow marked 5 is unidirectional. There is zero control from Earth on this mission. Okay? By law, an astronaut has to be watching it with the stop button, but the astronaut cannot actually do anything. Because this mission is so far from Earth, even if you sent a message to say there's a problem, and even if you could send back the instructions immediately, there would be a 40-minute round-trip delay. The entire mission is lost. There's also going to be collisions with individual of these spacecraft. There's also going to be collisions with asteroids. A lot of them are going to be damaged. They're going to have to reprogram themselves in space so that they can do what they need to do and contribute in some way, such as being a data transmission device. The first time I presented this mission was at a space conference, and I was the first speaker. It wasn't keynote, just happened to be the first speaker. And somebody at the back of the room stood up and said, "I'm glad to see we're starting this conference with science fiction." Okay? It's not science fiction. All of the technology exists. In fact, a smaller version of this mission is already launched. Not to L1, but it is launched. And by the time, as I say, it's launched, it's going to be better, faster, cheaper. It's going to be a lot more efficient. And we're going to be able to do a lot more with it. But this is the basis of many more technologies that will be developed in the future. A lot of the space geeks started talking about this when they heard about it and tried to accuse us of doing crazy things and things that were not possible. The materials used in this are carbon nanotubes, and NASA is the world's #1 manufacturer of carbon nanotubes, so it can be done. The technology all does exist, we just need to make it a bit better. So you see we get an article here from a long time ago, 10 years ago, from New Scientist, where they were talking about what we were building. People misunderstood it and accused us of trying to create drones that would kill people, which of course is not what we were trying to do by any means. The Times of London gave us a whole page article about what we were doing and thought it was wonderful. We got a lot of publicity out of that. And my late mother, at 81 years of age, got her first patent. I overheard her on the phone telling one of her friends what I do with drones, and I was like, this is not what we're doing at all. And then I thought about what she had described, and actually we were able to adapt it. And so she got her first patent at 81, she got 3 others after that, and she licensed them to NASA, and they are being used in the helicopter on Mars. So it's never too late to start with technology. So we've been working in 4 areas: formal methods, autonomic computing, software product lines, and automatic code generation. I'm going to talk to you about formal methods, and I'm going to talk very quickly about automatic code generation at the end. So we had a project called FAST, Formal Approaches to Swarm, where we were trying to identify what kind of notations do we need to be able to model these kind of systems. And we wanted to be able to model the systems in such a way that we could allow emergence, because that is the whole point of a swarm, that the total sum of the parts is greater than the individual parts. So you get extra behavior from these missions that you would not have gotten if you had specified exactly what it would do. So you need to be able to model it to see what are the boundaries. You need to be able to model it to see what areas are going to be problematic and what things do you want to forbid it to be able to do. So we came up with a sort of dashboard of existing notations, everything from CSP to X machines to probabilistic CCS, and they all, of course, contributed in some way. Probability wasn't such a big issue for us because we found that probability, we were doing something that we'd never done before, so the probabilities were really a guess. And many of the probabilities are tiny, and of course when you put tiny probabilities with tiny probabilities, you get such tiny probabilities that, you know, a factor of 100 makes no difference. So while we found existing notations to be useful, we didn't find them to be quite enough. So my former postdoc and now a faculty member in my department, came up with this language called ASSL, Autonomic System Specification Language. Somebody wrote to us after we published quite a number of papers on it, saying, I love it that you have a programming language with AS in its name. But the idea was that existing programming techniques and existing formal models don't really support the sort of things that you need to do in an autonomous system. An autonomous system has many, many more aspects to it. And we wanted to have that autonomy. We wanted to be able to do things that we didn't specifically say it could do. Of course, we don't want it to do things we specifically say it can't do. So we want to be able to define policies that can be used, that can be applied, that can be enforced. So if you like, they're a form of requirement, they're a form of correctness rule, but the point is that they need to be enforced for the entire system and for the lifetime of that system. So the idea was to create this language that would be suitable for self-managing software systems and beyond that as well. And it gives us a framework for being able to do formal specification, to validate those specifications, and to do automatic code generation. So the idea is that systems can be specified at 3 different levels. At the level of the autonomous system or the autonomic system, which is the term we like to use. People think IBM invented autonomic computing, but in fact it's a DoD term that IBM took up and supported. We also can specify the interaction protocols, the messaging between components, and we're talking about missions that have about 1,000 spacecraft. The reason for 1,000 is we know they're going to be damaged, so we expect only 300 to 400 of the 1,000 to survive, and it's too expensive to send more up afterwards, so we send enough to begin with. And we, of course, then have the level of the autonomic element, the individual components that are self-managing and that are being monitored, and of course, do the actual work. And we put all of these together at various levels, in various tiers, and this gives us support for the type of system we want to build. So here you see just a small snippet of the notation. It looks very like a programming language, which makes people feel comfortable, but it's not a programming language, it's a formal language. It has a formal semantics, and we can reason about it in various ways. And it has built-in primitives for the sort of things we want to do in autonomic computing or autonomous systems, able to say that things are initiated and terminated, and that things are done within certain time frames, and so on. So the toolkit and the tool set and the tool flow is fairly standard. The big advantage that we have is that we can generate different types of languages. Right now we have it generated in Java, but NASA doesn't use Java in flight. They want to use C++ and in fact a number of specialized languages. So we want to be able to generate other languages, but for now we're using Java because we're just using this for demonstration purposes at the moment. So the idea is that we have these various tiers and we build a tree internally that allows us to do various types of consistency checking and code generation. So we can just check for simple things like type consistency, which of course is a great way for debugging and for ambiguous definitions. But then we can check specifications and see that they're actually suitable, and then if so, we can generate code. The code, as I say, is being generated as Java right now, but we'll change that. So here's an example just of the interface to it, and in fact, you won't be able to read this, I realize, but the code here is a specification of the autonomous antenna on Voyager. Voyager is the oldest known running software. At least we think it's still running because it's now interstellar. We can't talk to it anymore, but when it went interstellar, it was still running. So it's more than 50 years old and by far the longest running software. It's been running continuously all that time. So we then are able to express things in first order temporal logic. We want to be able to express properties and then implement these properties in Java. And so we have problems here that we don't have a time built in, so that becomes a little bit of a problem for us. And we also have an issue with safety and liveness properties, because we want to be able to specify those, and we want those to be implemented. So for safety, of course, we want to make sure we don't deadlock, and of course liveness, we don't want to get into all sorts of spins. So we then want to implement various policies, and policies can be liveness and fairness as well, but we want to have policies that are essentially a constraint on the system. We have many policies, of course, but we want to be able to define these, and we use fluence, which is in the same terminology as von Neumann. It's basically long-lived functions. So we have functions that start and may end up terminating a long, long time later, and in between they're on and off and doing things. So it's really important that we have the trigger event and that we get the work done, but that these fluents can really be truly long-term lived. So we build up a specification tree, and then we're able to go and check through this for things like syntax errors, consistency errors, and so on. But again, as I mentioned, we don't have a notion of time, so we can't do the liveness and safety properties directly. So we need to consider how are we going to introduce correctness properties as a sort of a variation on policies. So it is easy to introduce errors because this is something that people are using like a programming language. As I said, it's not a programming language because it has a formal semantics, but it does mean that people treat it that way, and therefore they do write things that make no sense and do end up with things like daylights. So our solution to this is to do a form of model checking and automatic test case generation. So the idea has been, well, we could go and build our own model checker, or we could take something like Java Pathfinder and apply that in the framework. The problem with Java Pathfinder is that it has the explosion, the state explosion problem. Anything beyond about 10,000 lines of code doesn't make an awful lot of sense. And also, if you're using typical approaches to model checking, you're dealing with things at a very late stage. What we really want to do is to find things earlier. So we've looked at how we can build a model checking mechanism into ASSL itself. So I think I've already said what's on this slide here. So the Java Pathfinder, as I said, has the big advantage that it works on Java code rather than on a state graph. And it allows you to go through multiple executions of the program, check paths that are followed, check for violations, give you back reports on these, and give you back a counterexample. So that gives you the sort of traceability that you want to have. So this has been very much an inspiration for us in what we want to do and build in a Java model checker into this framework. So again, I think they probably said this. The state explosion problem, of course, there are many techniques in model checking, and some of you probably know much more about model checking than I do, but there are various heuristics you can use to reduce down the number of states, and we can actually do sort of an abstraction to reduce down the number of states and notice patterns, etc., and replace those. So there are a number of things you can do to reduce that state explosion. So the idea was to embed something like Java Pathfinder in ASSL because it's going to be a more specific for the framework. It's going to be able to handle the state explosion situation a little bit better, but we really have to still reduce it down. So essentially we build up this model checking approach that says we have an autonomous system, we have a specification that it's supposed to meet, we develop the state graph, an ASG as we call it, it's an autonomic state graph, and then we try to determine if the behavior of the system A matches the set of correctness properties P, and basically we do this using a cryptography structure. So we end up getting the constraints of P are specified in some sort of temporal logic because we need to bring in that idea of time, but we can decide what we're going to use, and we can change what we're going to use at a later point if we need to. So the idea is that we have this ASG represented as a tuple, the set of all possible tier states, the set of the transitions between them, the possible transitions, and of course the autonomic propositions that are part of that. And then we have labels that just map the states to the atomic propositions. So we end up having an embedding of something like this. Doesn't make a lot of sense probably if you're back in the room. So basically we want to build a model checking engine that enables us to show that certain correctness properties that have been expressed in an appropriate temporal logic formula are actually satisfied in the system, and that all combinations of the nested states satisfy that. So the problem is that we have all these nested states because it's an autonomous system, because it's a system that has so much going on at the same time and so much emergence coming from it. And so we're looking at how we can do this. We've been building our own engine, but it may be worthwhile integrating it with something that's already popular and saves learning a new notation, etc.
Sorry, what's lacking in the existing engines that you consider building a new one?
Sorry, well, the idea is that if we want to use something that's a bit more understood and a bit more well-known in industry, like spin, spin is very popular, then it saves learning something else and something new. Yeah. So then that gives us then a mechanism for reducing the state explosion problem of abstraction, and by prioritizing tiers. So we have tiers within the system that we can say, well, some of these are more important, or the probabilities that some of these are more important. That brings in the complication of probability again, that I mentioned before, which isn't always exactly a good thing. So essentially we end up with this sort of situation that we have our specification, we have our correctness properties that have been specified in some sort of temporal logic, we build this graph, the ASG, decide if it's suitable or not. If it's not, then we have to reduce it by applying heuristics again or probabilities, and then eventually if we're happy, we either give a counter, we either generate the code because we're happy, or if we're not, we give some sort of a trace that is a counter example of why this is not working for us. Our other approach is to generate code using a technique that we've developed called requirements to design to code, or R2D2C, and I have a little joke about that, I'll tell you in a minute. As engineers, believe it or not, like to write scenarios. And scenarios are appropriate for business and so on, but they're not really appropriate for the sort of systems we're talking about here. You can get away with it for things like satellites, but for the sort of systems we have here with so much going on and so much concurrency and so many components, it really just doesn't work. So what we're trying to do is to satisfy them in some way by generating code from scenarios, but by doing it in a much more formal way and with the formal methods basis. So the idea is, of course, we need various models because we can generate code using existing tools. We can extract models from existing code, not a problem. If we take the mathematical laws of concurrency as expressed by CSP or CCS or any of your favorite theory of concurrency, we use CSP because Tony Hoare was my supervisor, and that's why I'm biased towards CSP. But if we can reverse those, then we have a sort of a round-trip development process. We can go from requirements to code and all the way back again.
Sorry, is there a special language for expressing scenarios? Because we are using really text.
Well, that's exactly, at best they'll use UML, but they prefer to use English. And so basically we have a front-end natural language processor. So it has to be a constrained English, of course. But yes, and actually I'll show you in a minute, the whole point is anything you can parse is usable. So we've built this tool, and basically what it does is it takes scenarios in whatever way, generates traces from those, infers a model using a theorem prover, and the theorem prover we're using is ACL2, and that's a computational logic for an applicative common Lisp, and that's the successor to the Boyer-Moore theorem prover. And to be honest, the bias there is, first of all, we think it's one of the better theorem provers, but Bob Boyer and Jay Moore work with us, so it makes life a bit easier if you've got the developers and the inventors on your side. So then we can use a combination of existing tools and custom-built tools to do various types of analysis. In fact, we've built in automata learning so that when we generate a model from the specification, we get some what-if analysis type questions. We see which of these models are better. We can give feedback, and then using automata learning, generate other models that would be even better than that, or at least give us a larger choice of models to choose from. And then, of course, we can use the code generation from something like ASSL or whichever tool you prefer to use. So this lets us automate the entire development process, gives us better quality, lets us do formal proof about the properties of the systems we've implemented, do formal proof of correctness, and an automated means for requirements analysis. So what if we change this? What happens? And we can see that automatically. And then we have a guaranteed correspondence between our requirements and their implementation as code. So this technology has been licensed to one of the largest tool vendors, and it will be included in the next version of their code generation. I'm not allowed to say who the company is. We've used this in automatically generating provably correct systems, re-implementing systems after changes in requirements, re-exploiting reuse across platforms, because NASA doesn't use off-the-shelf chips. All the chips are developed for NASA specifically because they have to be low weight and low power. and those are generally custom made, and so we need to be able to reuse across multiple different platforms because the next mission will have a different chip. And we want to be able to reverse engineer some legacy systems and then to document those. Most NASA satellites are monitored by expert systems, which the rules were made in many cases 50 years ago, and nobody knows why the rules were developed as they were. So this gives us some way of understanding those rules and getting some sort of documentation for them. And then of course we can re-engineer existing systems to something that's much more manageable. So we've used it for agent-based systems, wireless sensor networks, but you can consider ANTS to be a wireless sensor network on steroids, or ACID if you prefer. And we've used it to verify the robotic procedures for servicing the Hubble. And the Hubble, as you probably know, will be decommissioned because JWST will replace it. The Hubble is roughly the size of 3 buses. Originally, the space shuttle was designed so that the Hubble would fit inside its cargo bay. When the Hubble first went up, its solar panels didn't unfold correctly, so they had to be replaced with fixed panels, and then it no longer fit inside the space shuttle. So the original idea was that it would come down every 5 years and be physically upgraded. Now that can't be done. So there was a requirement to keep it going, to have a robot go up and make the necessary changes. In the end, it became a robot and astronauts because they just didn't trust the robot. But basically, it was 5,000 pages of instructions as to what the robot should do. This is the first page of it. The first column is timing constraints. The next column is the grapple arm, which is the large robot arm. And then the next two are the dexterous arms, the smaller arms, which eventually became astronauts. The problem is that this took 5 years to develop, and when the launch happened, there would be 11 minutes every 90 minutes where you couldn't see anything. So the robot couldn't be doing anything risky, like lifting out lenses, opening doors, taking out batteries during those 11 minutes. And the robot could only run for 8 hours and then had to charge for 16. So there were really serious timing constraints. And these had to be recalculated once the mission launched. It took 5 years to do it originally. So these basically had to be recalculated in 24 hours. So we decided to use our tool to do it. If this looks like Microsoft Word, there's a good reason. It is Microsoft Word. Okay? The advantage of Microsoft Word is that you can tag it, and then you can read it into the tool. So what we did was take Microsoft Word, turn it into CSPM, which is a machine-readable version of CSP, and then we could run it in our tool. So our tool is called R2D2C, and again, you probably can't see it at the back, but the logo up in the top left is the R2D2 robot with a big C around it. And I called Lucasfilm, and when the caller ID says NASA, people answer the phone. So I actually spoke to George Lucas, and he gave us permission to use the robot as our logo. Not for commercial purposes, but for internal. So when we ran this, we kept getting crashes. It kept crashing in the first few seconds, and we thought, well, this is because it's a prototype tool. You know, this isn't the real thing. Okay, maybe we need to make this a bit more robust. But we actually discovered that the tool was crashing because there was an error on the first line of the 5,000 pages. Okay? I assumed they would have found it by other means, but it was great that we could find it so quickly with our tool. So these technologies will be used in Artemis when it does launch, possibly next year, we're told, or the year after. I think probably that's a bit ambitious. I think maybe a few more years, but it will be used. The rocket testing actually passed last week, so it is actually coming on pretty soon. Just a caveat. Just because we can do things nicely on paper doesn't mean that it scales up to be these huge missions. But it's a starting point, and we have to start somewhere. And so for every success we have, we'll have probably multiple failures, but at least we'll get there. So that is the intent. So thank you very much. That's all I wanted to say. I will just say a shameless plug. If you're a member of IEEE and based in Europe, Middle East, or Africa, I am running as candidate for director-elect. So if you please consider voting for me, I would be very grateful. So these are images from the Hubble Space Telescope, and they are real images.
Okay, thanks a lot, Mark. This was a very interesting talk. And I'm sure there are some questions from the audience. Yes, please. I give you the microphone.
Can you hear me? Yeah. Thank you for the nice talk. It was entertaining. I have some question about your temporal logic that you use. So first you say you take the temporal logic and then you throw away all the temporal operators. Or you just throw away a subset.
No, the idea was to use a first order logic, and then we say, well, yeah, but we need time, so we need to change that. So it's actually the opposite. We start with first order logic, and then we decide we need to add time.
Okay.
Yeah.
So do you just select something like next, and you throw away until and since and those kind of things?
Sorry, I can't quite hear that.
You had a slide where you said throw away, I think you had since, until.
Yeah, we don't have those in the language, so that's what we need to add them. Yes. Yeah.
And then the second question is about this language SSL. Should I think of it as a real programming language only, or also like doing specifications? To me, it reminds me a little bit.
I'm sorry, I'm really finding it hard to hear you. I don't think the mic is on. Oh, that or the speakers have gone the wrong way.
So I'm not maybe another way.
Now I can hear you.
So this language is ASSL, I don't want to say the other way. Can I see it as a specification language, something that defines which actions are possible?
Yes.
And then the way in which you program it doesn't really matter, what's different. The way in which it executes.
Well, it is a specification language, but it has some primitives that would be useful for autonomous systems. And yes, you could just decide, write the specification and then go program it to suit that using various means. But it also has a built-in compiler that will generate, as of now, Java, but the intention is to generate multiple different languages.
And how far is something like a planning description language, like PGL?
It's quite different because it's built in other primitives. A planning description language is similar in the sense that it has, it has the semantics, etc., but we're looking at building something that's much more specific to autonomous systems. So, I mean, all specification languages have their advantages in various ways, right? It's whether you use it for particular things. And as I said, we had done surveys of notations that we could use for these types of systems, and none of them did it, right? All gave us bits and pieces that are all useful, but nothing gave one single picture. And that was the whole idea of developing this, that you have a single language that would do everything in these. So we're not there yet, but we're getting there.
Okay, there are other questions? No other questions, then I put a question.
No, I will not tell you what the entire talk was in one sentence. I was going to ask you that this morning, actually.
So my question also concerns the temporology aspect. So you said that the state explosions, of course, the fundamental problem. You said you use either abstraction or parallelized tiers.
Yes.
But there are also other techniques.
Of course there are multiple other techniques, yeah. Exactly.
And why don't we use others?
Well, we can, but these are what we're working on at the moment, but yeah, we can use them.
I'm surprised these are not so impressive.
No, but we have to start somewhere.
Okay.
But yeah, absolutely. I mean, I don't claim to be an expert on model tracking by any means. There's lots of other things we can do.
Yeah. Okay. If there is a question, then we thank you again.
Thank you.
As we meet our